Hi. Welcome to Smart Academy online tutorials. So we have our official website on Facebook and we have our official YouTube channel on YouTube. And you can always support us by subscribing and following our website on Facebook. And we always appreciate. Alright, so in today's class, we are basically looking at dimensional analysis, natural science class. Okay. So, what do you understand by dimensional analysis? I'll be abbreviating, I'll be using DA. So, DA means dimensional analysis. So, dimensional analysis is just the analysis of relationships between fundamental physical quantities. So, we're talking about the fundamental physical quantities. Fundamental physical quantities. What are these quantities exactly? So fundamental physical quantities, so we'll just be dealing with the mass, length, and the time under dimensional analysis. So we'll be dealing with the mass, length, and the time. So these are the physical quantities we'll be dealing with under dimensional analysis. So before I give you dimensional equations, I want you to understand how do you use now this same dimensional analysis. So dimensional analysis, it has uses and it has what limitations. It has uses. So one of the powerful tool or the use of dimensional analysis, the uses. First, I give you the why is it important. Dimensional analysis as you study this topic. So dimensional analysis basically one this one you can use it to change from one unit to another. So one thing is changing from one unit. So it is used when you changing from one unit to another. So it is used when changing from one unit to another unit. So for example, let's say we have 20 we have 20 kilometers per hour. So we want to change this 20 kilometers per hour to meters per second. How do we do it? So we're going to say 20 kilometers over 1 hour is as good as this. So we will say, since we know that 1 hour is actually equivalent to what 60 minutes, okay, you can even put small brackets so that you look smart what you are dealing with. Then we know 1 hour is equivalent to 60 minutes, and 1 minute is actually 60 seconds. 60 seconds, okay, and we know that 1,000 meters is equivalent to 1 kilometer. So you can cancel out the spectators. Okay, so they like terms we can say. So we have kilometers and here we have the kilometer, we have an hour here and given here we can cancel. So we are remaining with it. So even here we can cancel minutes and minutes. So you are remaining with on the numerator we have meters, on the denominator we have now seconds. So it's just a matter of now you multiply. So if you multiply 20 by 1,000, this will give you 20,000. So 20,000 meters over. If you multiply 60 by 60, that would be 3,600 seconds. So these are the units that we are remaining with. So if you are to divide this, okay, if you are to divide this 200 by 36 to give you, let me just divide just so let's say 200 we divide 36, so this will give you this number. Okay, so 5.5555. Okay, so this will just get three significant figures. That will be 5.56 meters per second. We've converted. So that's one use of dimensional analysis. That's one use of dimensional analysis. Okay, so another use of dimensional analysis is also used to derive relationships among several quantities. So we can use it to derive relationship. You can use it to drive relationships. So dimension analysis, you can use it to drive relationships. Then other uses, there are even other uses you can go and start further. So other uses you can even put is used to check, and this is very important. It's used to check if an expression is actually dimensionally consistent or there is homogeneity, or what I mean, if it's equal, right? Let's look at the limitations now. Let's look at the limitations. Let's look at the limitations. Okay, so now let's look at the limitations of dimension analysis. Okay, so even like anything has limitations. Yeah, actually, even the dimension analysis has limitations. The way Samson had a lot of strength in the Bible, you know this story. But his limitation was his girlfriend, Delilah. Okay, you know this story. Okay, so now let's look at the limitations of dimension analysis. So one of the limitations of dimension analysis is that dimension analysis is only applicable to three dimensions. So this one is only applicable to three dimensions. So it's only applicable to three dimensions. And what are these dimensions? I mentioned them in the definition of dimension analysis. So these dimensions were what? We have length. So when you write the dimensions of dimension analysis, you need to put them in the square bracket. So for length, the dimension of length is actually L, capital L in square bracket. Then time, you have time, capital T in square bracket. And you have mass. Okay, so these are the dimensions. And you have mass. So capital M in square bracket. Capital L in square bracket. Hope you guys are following. Yeah, you understand it. Then, secondly, we have one of the limitations is dimension analysis does not give the value of constant. The value of the constant does not give. Dimension analysis does not give the value of the constant. Okay. The value of the constant can only be known when the experiments are performed or when the experiment has been done. So in the question, they can actually give you the value of the constant. Yeah, when the experiment is being done already. Then another thing is limitation of this GF. So it's not applicable to logarithmic. So it's not applicable to logarithmic, exponential, and trigonometric functions. Trigonometric functions. Okay, so you need to understand. So this one is not applicable to logarithmic, exponential, and trigonometric functions. Not applicable to this. Okay. Next getting. So dimension analysis is we cannot derive more than one part of an equation. That's one of limitation as well. You cannot derive more than one part of an equation. So what do I mean when I say you cannot derive more than one part of the equation? So let's say you have this equation, the skeleton equation. May I go to the skeleton equation? S being equivalent to the new u, then t, okay, plus 1 over 2 a squared. So for dimension analysis, you can't deal with this everything at once. No, you do it independently. So if you are doing this, so we can only derive this part independently, and for this part s and this, or we can derive s being equal to 1 over 2 a squared independently, not at once. So this can only derive relationship between this AC and this, or this AC and this 1 over 2 AT squared independently and not at once. Then another important rule that I want you to understand is one very important rule that you need to understand is we only have one very important rule, and this one is you can only add, so you can only add or subtract, you can only add or subtract items with same dimension. Okay, you can only add or subtract items with same dimension. Let's say, let's say we have this of a, okay, of a minus b. Okay, of a minus b. So meaning since we are subtracting a from subtracting b from a, since meaning a and b, since they are having a minus sign in between them, then the dimensions of this a and the dimensions of this b, they are actually the same. They have the same dimension actually. I mean the dimension of a is actually the dimension of b. That's what was under this rule. We can only add or subtract items with the same dimension. Okay, now I've come to the very important part of this video. So if you didn't pay attention to the intro, make sure you pay attention to this part. The step taken to derive any equation. The step taken to derive any equation. The step taken to derive any equation. Okay, in writing, steps taken to derive any equation. Okay, step taken to derive any equation. So the step taken to derive any equation. So step one. Let's say you have been taught to derive an expression for an acceleration if it is related to the velocity and the radius. Okay, let's say you have been taught to derive an expression for an acceleration if this acceleration is related to velocity, which is v, and the radius r. This is the equation. Let's derive an expression which is we derive an expression for acceleration. Then this acceleration is related to velocity and the radius. So what you need to do is you write a acceleration, then a proportional symbol, which is alpha. Okay. Then each quantity will be placed a letter of the choice. Each quantity will be placed a letter of the choice. So if you write alpha, if you write a, then write the symbol, proportionality symbol is alpha. You multiply with b, then you multiply with r. Then each quantity will be placed a letter of the choice. You can even use small letters a, b. For instance, here I will just use x and y. I've raised it to the power of x and y. Then step 2 actually what you will do is you will replace the proportionality symbol here with an equal sign. Replace a proportionality symbol with an equal sign. So we're going to say a is equal to. So if you replace this symbol with an equal sign, instantly you need to introduce what? A constant. So introduce constant k. Okay, so if you replace alpha, you will introduce equal sign and constant k. Then so it will be like this. Alpha, acceleration is equal to k, then multiplied by v, the power x times z, actually add the power y. As simple as that. Okay, hope you guys can follow it. Then step 3, you need to replace each quantity with its SI unit. So you know the SI unit for acceleration, for velocity, and radius. Okay, so for acceleration, we have the expression acceleration is equal to constant, we have v to the power x, we have r to the power y. So acceleration, we know that is meters per second square. That's the SI unit for acceleration. You can even put in small bracket. Then k constant, no unit, constant, there is no unit. So velocity is meters per second, the power x. Then you multiply by radius, radius is distance, so SI unit is meters, then you raise to the power 1. Step 4. Yeah. Step 4, what you are going to do is you need to put the appropriate dimensions for each unit. So, remember dimension analysis, we only deal with dimensions, what is length, mass, and time. So, let's say for this meter, so the dimension of meters, which is length, we're going to use L capital L in square bracket over T in square bracket. The square should be outside. Then it will be equal to K constant. Then L, now is then T in square bracket. Everything raised to the power x. Then you multiply by. Then for your radius here, which is meters, so meaning you're going to use L in square bracket raised to the power y. Then what you need to do here we're going to distribute x on the part of the numerator and the denominator here. So we're going to say L here over T squared will be equal to constant. Then we distribute, so meaning this dimension of L of the power of x over the dimension of T as well, so the power of x, and we multiply by L, okay, like that. Okay, the steps are very simple and you follow them. They are very simple, okay. The steps are very simple. Okay, now since you have distributed the x, what you need to do right now is to make all dimensions become numerators. So make all denominators all the denominators should become now the numerators. That is step number 5. I want to say make all denominators become numerators. Okay. Ensure that when you are changing from denominator to denominator, ensure that even the sign is changing. Okay. Yeah. Let me show you what I'm saying. Okay. Let's say we have b, okay, over t, the power t, equal to constant k, L, the power x, over t, the power x. Then you multiply by L, the power y. Okay. So what is happening here is this. So when I say you need to change all the denominators to become numerators, I'm saying if you write L, if you change this one to become numerator, meaning to have a power of -2, it won't be positive 2. Meaning, when I said you need to take note or take care of the change of the sign. Okay, so that is t to the power -2 will be given constant k, then we have the length, then x, okay, then t the power -x, the sign has changed, take note. Then we have L at the end, dimension of the power. So what you need to do is this: you need to put like terms together, like the way you create convolution block. Yeah? The way you create them very nicely. Okay, so that's how you need to do even here. Create the like terms together. Okay, so let's say here we have L. Okay, so when L can be written as good as this. So L to the power 1 is actually just the same thing, right? Yeah, that's the same thing. So raise it to that power, and even t here to the power -2 of constant here, k, okay, and here we have L the power x. Here we have we'll put like terms together. Okay, put like terms together. We'll put like terms together. Okay. So if we put like terms together, so here we have L to the power x. So we know here we have L to the power 1. then we have t. Okay, t to the power negative a. So these are like terms. So meaning like terms we can even add actually the exponent or the power maybe power. So these are the exponents. So we have the the power 1 t the power negative 2 will be equal to constant k. So we're going to say L then to the power x plus y, then t the power negative x. There is a multiplication symbol here. You can just put a dot. Then after this, what you need to do is after this, what you need to do is you step 6, you equate the powers. Equate the powers. Okay, equate the powers. Sorry. So you equate the powers. How do you do it? So you equate the powers on the left hand side, on the left hand side to the right hand side, and the powers of L on the left and right hand side, and the powers of T on the left and right hand side. So the power of here of L and here of L. So the power of L here is on the left hand side. So this is our left hand side, and this is our right hand side. So on the left hand side you have 1. So 1 will be equal to x plus y. You have equated. And the powers of t, we're going to say we have negative 2 here. So we're going to say negative 2 will be equal to negative x. Then we can find now the values of p. Okay, find the value of x. So here we're going to divide by negative 1, blah blah blah. X will be positive 2. Simple. Okay. So then if you want to find the value of y, what we're going to do, you just substitute the value of x here on this equation. So we're going to say x plus y is given 1. So meaning the value of x is not 2. So it's 2 plus y is equal to 1. So y should be 1 minus 2 and your y should be negative 1. Simple, right? So we have the values. The value of x is 2 and the value of y is negative 1. Again. Yeah. Okay. Okay, now step 7. So this is the final step. How you should conclude with this when deriving the expression. So these are one of the uses, like I said. You derive the expression when it's related to something. Okay. So step 7, you replace the letters to this equation. So a, the expression of a equal to k. So this is the equation k is equal to v then to the power of the multiplied by r the power n. Now we have found the values of x. X is 2 and y is 1. So since these values are found, we're going to replace them on this expression that we made. So what we're going to get is acceleration is equal to the constant k, v to the power, our x is 2, and r to the power negative 1. So since this r has a negative, so this part, this whole thing here can be written as a denominator, substitute as a denominator. So we're going to say h is equal to constant k, then v squared over r. So this is our expression. We have derived our expression. And from experiment, if they mention to say maybe the question to say experiment, when experiment was done, our constant was 1. So if the constant was 1, we can even put here. So our expression is equal to 1 multiplied by v squared over r. So meaning if it's 1, we're going to say expression is equal to v squared over r. Now it wasn't anything, I'm just saying, okay, sometimes they give you a constant. Say a constant is v. Alright. Let me give you the question for you to just go and try. Okay. I want to justify the values actually. Not a tough question. Okay, just to see if you have understood this part. Okay. Then next day, focus on math. Okay. Assignment. assignment. So assignment, I want you to do this. I want you to find the values of x, y, and z. In this expression, I'll give you the expression you don't need to derive. We have v equal to p, then p to the power x, then law, this is law, which is density, the power y, say y, then v the power z. If v is actually p, if v is p, and if p is pressure, and if law is density, and volume, v actually is volume, okay, and p is a dimensionless constant, okay, and c is a dimensionless constant. Find the values of x, y, and z in this expression. V, p to the power x, we have the law here to the power y, v to the power z. If this v is p is pressure, and rho is density, v is volume, and p is a dimensionless constant. Okay, let me just give you maybe the idea here. So the key thing is to understand the unit of each component and reducing that unit to its simplest form involving length, mass, and time. Okay, so we know the volume is meters per second, the pressure is newtons per meter square, and 1 newton is actually equivalent to 1 kilogram per meters per second square. Fortunately, the question simplified the units for us in this case, and the law is density. Density is in kg per meter cube. Okay, and volume is meter cube, and C has no unit, it's a constant. C will not have any unit, just like the way you don't have the Kelvin. Okay, so now the expression has been given to you. So meaning here on the expression, the C can be ignored. I'm giving you a little, the C can be ignored here. Okay, and you proceed with the expression. I just want to find the values. I see the values if you're going to find the correct, if you have understood dimension analysis on this part. Okay, otherwise, thank you very much for your time, and see you in the next video.